Okay. Well, welcome. We are going to have another version of the NeSI infrastructure. We've been hearing about a bunch of the research that's been going on, so I wanted to give you a little sneak preview of what we have been thinking about. And so let's get going. And the goal of today's exercise will be, at the end of the talk, we'll be able to look through this equation and come up with an answer to it. And by that time, you should be able to figure out what all those different digits mean. It's actually not that complicated. We here in New Zealand have some natural advantages, especially in the fight against COVID. This was pretty dramatically demonstrated in December. My wife and I took a trip up to Cape Reinga, and you see the mixing of the Tasman Sea and the Pacific Ocean. Yeah, it's this really isolated place in the world, and that's served us well. But you can't just be isolated and have that take care of it. In the keynote today, we heard a lot of work that went in on top of that to make this happen. So we in the HPC world, we've got a lot of advantages in terms of what's going on, being able to buy new hardware, but we got to do some work on how we can best take advantage of that. And that's the whole theme of this talk here. I mean, this is, I'll say, the history of most of high-performance computing, at least when they started tracking the top 500 back in 1993, a very familiar plot. The red line is the very lowest entry on the top 500, but even that one goes up through several orders of magnitude through the years. And that's probably more typical to the type of system that we at NeSI would purchase. There's some newer machines in there as well. But what's interesting about this, having been an observer, and as I think many of us have been, there have been different drivers that have happened through the years, whether it's just clock speeds getting a lot faster, or there was the so-called massively parallel processing phase. There was a lot of innovation in the blue gene area. A lot of economy of scale then when the x86 processors got popular enough. GPUs have been a really big driver lately, and of course the number one system now is driven by ARM. So there's all these waves of technology, and which ones can we at NeSI use right now to produce the best system? Now, if we go back to when we purchased the current systems, I mean, the studies that we put together, you can see this goes back to 2012, 2014. The usage patterns were, on one hand, we had a lot of just single core, single processor jobs, and that was a capacity type machine. We had some others that scaled way out. So we decided to purchase a capacity machine and then a capability machine. And that is exactly what's on the floor at the computer room at Greta Point. On the left hand, you can see the Mahuika machine, the capacity machine, and there's the storage in the middle. But on the far right, that's the capability machine, the Maui system. Actually, there was a tour on Tuesday. Some people from this conference went. We've got another tour available Friday. So if you have some time after the conference, before you fly out, you can still sign up. I think we're about half capacity right now, and tour the facility. So you're welcome to join that. It's always an interesting visit. Turns out that when we at NeSI put these machines in place, the old system, this is a plot of usage, and on the old systems on the far left of the plot, they were being used, the PAN system was up about the 80% usage level. We did put I'll say a temporary machine in place to take the load, and that rapidly filled up. But then we started with the Maui and Mahuika machines in 2018. And we thought it would take about 3 years to fill them up and get them up to capacity, but it turns out that we were more successful, or our users were happier or more successful than expected, and pretty much filled the machine up to about the 90% plus usage level in just 2 years. So we've really got to find more capacity for the system. So that's what the effort has been. The other good part of this is that the two different machines are on a different financial model. Maui they're both set up for a 6-year expected useful lifetime. and Maui, we're building up funds to replace that after 6 years. But the Mahuika machine is actually set up to have basically a replacement after 3 years. Now, obviously, COVID has been a really big impact. So rather than spend all that money right now, because our funding partners are primarily academic, they were more than happy that if we could just spend part of that money this year. So this is a partial refresh of the machine that we've been looking at. So let's look at what happened since we put out the last RFP in 2017 to what the new RFP is going to be like this year, and see what we can get for our money. There's basically 4 main areas that we can talk about. The processors back then, the best things out there really were the Broadwell and Skylake processors from Intel, 18 or 20 cores. Now, Intel is about to come out, we think, with Ice Lake, and I think in the HPC area, about a 32-core system will be about, chip will be about the most popular, but they do have even some larger ones that may be more interesting. AMD is about to start delivering their Milan processor soon. That's at 64 cores, so there's obviously been a big increase in that area. Memory used to be 4 channels of memory at a certain memory speed. We're up to 8 channels now to give a lot more memory bandwidth and feed those processors, and the clock speed has gone up correspondingly. Our systems are connected by InfiniBand. There was a mix of EDR and FDR systems, 100 gigabits per second. Since that time, Mellanox, now NVIDIA has their, they got a reverse here. Yeah, they do have a 40-port switch. That's not QDR, so that's my first typo of the day, but it is 200 gigabits a second. And then the GPUs, we've been sitting on some NVIDIA P100 technology for some time, and we skipped to the V100 area, but we've both got options from NVIDIA, the new A100 and the AMD MI100. So there's, as typical in the HPC world, we've got a lot of advances and building blocks that will allow us to do really great stuff. So if we look into more detail on the processor side, we think that the most value we can get is going from the Intel to the AMD Milan version, but we're open to an Intel option there. The memory, we are obviously going to go up to 8 channels at the faster clock speed. We had a bit of a debate about the memory DIMM size, but if we go with the 32 gig DIMMs, we'll actually have more gigabytes per core than we had the previous time. Our data shows that actually the users are using far less than 4 gigabytes per core. I think we could get by with some, but that might just get us in trouble. Clock speed, of course, is one thing that is not going up very much, but when you cram all those cores onto a chip, the thermal properties can go up from a target design point of 120 all the way up to 200 watts or so is what we expect. But the real measure that we're using here, we think it's very representative of the workloads for the capacity machine, is the spec FP rate. And the per core rating, for the system we have now is about, 3.7 if you do the math, and it should be actually quite a bit more on the AMD or the Intel processor. So we think we're going to get a lot more work through on this new machine. If we looking into the detail on the interconnect, as I said, here we fixed the typo. I fixed the typo. Rather than FDR, EDR, we're at HDR, which in the full HDR is this 200 gigabits a second. But there's this HDR 100 option where they split the signal into a couple signals. And actually, this is the key thing that makes this actually quite wonderful. When they went up from 36 to 40 ports in their switch, it didn't seem like very much. But actually, those 40 can be split into 80, essentially, of the 100 gigabits a second. And so going from a 36 port to an 80 port switch just gives you all kinds of flexibility. So myself as an architect, I'm in love with that. And the latency, I kind of made up these numbers today because basically the latency is going from really low to even a little bit lower. And latency numbers that you see quoted here are somewhat bogus because it's like a zero-length message. We don't send zero-length messages, but latency is really not so much of an issue. Actually, bandwidth isn't so much of an issue. We have plenty of bandwidth at the 100 gigabits a second, so that's why it's just fine to take advantage of that split signal. This is a chart I lifted out of the Next platform about all the innovations in the GPUs. On this screen, you can't read anything, even big fonts here. But the message that I'm just telling you is that if we go from the far right, which is the P100, which we have, to the far left, which is the A100, which we're actually, we've got a couple test GPUs that we're installing in the system right now. NVIDIA has done a great job at putting all kinds of new capabilities in, from the tensor cores to everything else. And I'm just mainly a hardware-focused guy. There's been so much software advancement as well. There's going to be all this great new capability in the GPU front. So we're actually looking for users who want to show us how wonderful these new GPUs are going to be. So contact your favorite NeSI staff member if you're able to. This is just a picture of how we have the systems connected right now. That big block in the middle is the Mahuika system. It's got 9 switches holding all the nodes that tie into 4 core switches up at the top. Fortunately, there was a little bit of room still on those core switches, so I've been able to, just to the right in the compute area, put in a new set of compute nodes. And in the future, on the far right is our current ESS disk, but we even have room for a disk addition when more of that money's released, and we want to grow our storage as well. So we think this is all actually going to fit together quite nicely into the existing system. Okay, so all this sounds wonderful, but there are pitfalls. On the same day that we went up to Cape Reinga, we stopped and saw actually what was the biggest industry for some years in New Zealand, which is the gum diggers, digging holes, hoping to find kauri gum. And you just got to be careful about walking through the woods here because you can fall in one of these pits that are still there. And so we've got obviously some issues that are possible with this new system as well. The first one I've mentioned, we're on an Intel-based system. We're likely to move to an AMD system. I talked to my colleagues here who help the users compile the codes and such, and they think that is going to be pretty standard, that we should be able to handle that pretty well. That's not that complicated. Another pitfall is that we've got the storage bandwidth. We used to have those 9 switches connecting the current machine with lots of, that's 9 times 4, 36 connections up, 36 wires to carry the I/O up to the core switch and over. Now we've just got 4 connections. So we're going to be watching our bandwidth. We actually do have a backup strategy. We could just unplug 4 nodes and basically double our bandwidth as well. Okay, last thing, there's a little bonus area. When you drive up to Cape Reinga, everyone talks about the 90-mile beach over on the one side of the peninsula. Well, over on the right-hand side, there's the most beautiful white sand beach. I just didn't read enough guidebooks to learn about that. But that was a bonus on that trip. A bonus here is that we've got this this capacity machine, and the extension that we're putting in actually makes it a capability machine. On the left is just a cartoon of those 9 switches and the cores that we have connected. I mean, we got 8,000 or more cores, but they're loosely coupled with an 8-to-1 interconnect. When we have everything going through that one core, we're going to have 9,000 cores, and it's going to be a very tightly coupled 1-to-1 system. So it's going to be a great machine. And it all fits in one box. So the answer to the equation, when we multiply out all the cores and the spec FP, we think that this, on the left-hand side, are the 4.5 racks that are currently comprising the Mahuika system. On the right, we should be able to package all this into a single rack, and we should be able to get 1.23 times the compute capacity. So actually, we'll be able to more than double the compute throughput with that one rack. So thank you much for your attention.
Questions for Jeff?
Thanks, Jeff. You will achieve that 1.23 changing everything Intel into AMD? Or that you aspire that? And just following it, a totally curiosity, the question, you're a capacity provider. You are not, are you going to experiment, I don't know, with RISC-V or any architecture just to play a little bit?
Well, I love like different architectures like the new Fujitsu machine, the Fugaku machine based on ARM. We thought that this is really kind of a moderate extension or expansion of the current machine. We didn't want to go too far, so we wanted to stay in the x86 world. And yeah, I mean, this is the number that we would calculate, we expect roughly with an AMD solution. You know, Intel might be able to give us the same type of thing that with some economic incentive and such as well. So you know, we'll see where this really lands. I think when in 3 years from now, when we do the full system refresh, then we'd be consider something, you know, more radical in terms of.
So today is a procurement exercise.
Right. Yeah.
Yeah.
Yeah. This is kind of a preview of what we have planned, and and here or at dinner, I'm very happy to take comments and suggestions if anyone has or more questions as well.
I guess I have a question, Jeff. I often, so engagement manager, I am out talking to the researchers.
Yeah.
What is the biggest win for the researchers out of this development?
Well, there's two. I mean, one is just basically, you know, now we're pushing the capacity of the machine. You know, this will give us a couple of years of breathing space. But then there is that. There's three really. There is that you know, as I said, since they're tightly coupled, people could run scale-out codes on this system. Now, I didn't spend a lot of time. You know, this picture I have, the cartoon on the right, the purple one, the top darker block is just a little networking. It's mainly the compute nodes, but at the bottom there are 4 nodes with the new A100 GPUs, and that's going to be a huge change. And we might need to buy more of those in short order in case they prove popular. But we just want to make sure the timing is actually very good for us to, you know, to have the chance to buy something. And even though NVIDIA announced these A100s about almost a year ago, you know, they're just really becoming available now where we can, and so the timing is very good for us to be able to jump on that right away.
Are you affected for the scarcity of chips?
I don't think so. No, when chips, you mean memory chips, processor chips, GPU chips? Yeah, I mean, yeah, I mean, I think, you know, just like with any hardware or software project, I think, you know, there are delays, but as I said, actually our timing is actually coming out really good because both AMD and Intel have new processors. NVIDIA is just able to deliver their new gear. You know, we're very happy with the interconnect part. That's tried and true by this point. So.
Cool. Well,
Okay.
thanks, Jeff.